This is my second video on pointers and arrays. If you haven't seen the first one, you may want to review that first to help some of this make more sense. So we can certainly declare two-dimensional arrays in C like this. So this says I'm going to have a 3x4 array of ints. But in order for us to understand how this is stored, it's better to think of this as being an array consisting of one-dimensional arrays. That is, data consists of 3 arrays of integers, each of which consists of 4 integers, as opposed to thinking of it as being a 3x4 construct. So here's my question to you. How are one-dimensional and multi-dimensional arrays stored in C? Turns out the answer is that they're stored the same way. May not believe that, but let's see. So we'll call function A, void. And I'm just going to put all the code here. So let's have int x 1, 2, 3, 4, 5, 6. So I have 6 numbers. Because I want to print out the array for I equals 0, I is less than 6, I plus plus. And we'll print the number. We'll say it's 2D because I know where I'm going with this example. And %p, which means I need an address here. So what I want to do is print each of these 6 numbers followed by the address of that number. One through 6, and since these are ints, I know they're 4 bytes from each other on a modern computer. So the first one's at address 40, so we go 40, 44, 48, and so forth. So I can tell these are 4 bytes apart, and of course arrays are stored in contiguous memory locations, which means they're right next to each other. Let's create another function. We'll call this B, but this one now will be a 2x3 array of elements. We'll print them out. So now we have 2 rows, 3 columns each. Don't really need the formatting, but I'm doing that to make it more clear. All right, so let's see what happens. We should get different addresses this time. And let's make a little change. I'll just line that up, don't really need to. And we'll say so we did get different addresses, I think, because I don't remember the 5s being here. So once again, for the top one, print the numbers 1 through 6. And here's the addresses, 40, 44, 48, and so forth. And then I print the second one, and what happened? There's those numbers, 10, 2, 3, 4, 5, 6. I could change the other 5, but I don't need to. And even in this case, you can actually get the same addresses. Why is that? Well, in a later video, I'll talk more about the stack and the heap, but just realize basically what happens here is that when main calls A, the flow of the program comes up to here, It's creating a bunch of variables and doing things. But basically, when I get to the bottom of the function and return back down to here, we should assume this doesn't exist anymore. In reality, what happens is the spot in memory where this information is stored is available to be overwritten. So then when we call B, this information is being overwritten on top of this. So it happens to use the same addresses for stuff. So this is no longer there. Now we see this. But I shouldn't necessarily assume. It depends on what I'm doing. I could do other things here that would prevent my new array from using those exact same spots. But that's the way it worked out in this case. But what I'm wanting to get at is that here's the 3, here's the 4, just like up here. For 3 and 4, my addresses are 4, 8, and 4C. Down here, 4, 8, and 4C. This says the 4 is stored in memory right after the 3. You would think if this was like some type of two-dimensional construct that the 4 would be stored in memory right below the 10 on a new row. But it's not. It's on the same row. Let's look at another example. This one would be a 3 by 2. And I'm deliberately picking things that use those 6 elements. I'm going to put a 20 this time so we can see what it looks like. 3, 2. Because now I have 3 rows and 2 columns each, and I need to actually fix this. Actually, there's certain things I could do, and I wouldn't actually have to change it. So first row, second row, third row, and I'm calling C. Overall, the address has changed, but each of these look like they're using the same 6 addresses for each array. Here's the first one, start with 1, then the second one in function B has 10, and now this has 20. Which shows they are different numbers in the same spots. But once again, they're in contiguous memory locations. So that means right after the 2 in memory is the 3. Right after the 4 in memory is the 5. And finally, since we have these 6 numbers, I'm going to have a 4th one. This array D is going to be a 6 by 1 two-dimensional construct. I don't really need to line all these up, I just chose to. So now this needs to be fixed, and now say 6 by 1. I could actually just hard code because each of the second element, because each of these is in column 0. Oops, and what did I mess up here? Need a comma here. Overall, the address has changed. But the relationships between the numbers is the same. Contiguous memory locations. All right? And in fact, I don't even need these inner curly brackets for what I'm doing here. Let's add one more just to prove that to you. Let's do... this will blow your mind. I don't need to put these in order either. I just do make it for readability. And this time this will be, we'll change this to 99. Wow. How did that work? I wrote it like a one-dimensional array, but by writing the two sets of sizes, this is what imposes the structure on it. So that way I can refer to it with 2 dimensions. So if I want, say, the 4, so I'm saying it's 2 rows and 3 columns. So if I want to get the 4, that means this is row 0, column 1, column 2, row 1, column 0. So X row 1, column 0 should give me the 4. And there it is. So how's all that work? Well, it's actually stored like this. So when I write int, say A equals 1, 2, 3, 4, 5, 6, right? Of course, it's easy to think of this as being a 2-dimensional construct, but let's say BF00 is the beginning address where 1 is stored at. And what about the 2? Well, that's 4 bytes away, BF00, because for 1, this covers the addresses BF00, 01, 02, 03, and now this, would be 4. BF08 would be the 3, and so forth. But if I do this, int B, square bracket 2, square bracket 3, and technically I can leave the 2 out if I set everything up properly. That's when you can potentially have issues. 1, 2, 3, 4, 5, 6. What I'm telling you and what I just demonstrated in my program is this right here is stored this way as well. So that means 4 is right here at BF0C. And 5 is BF10, and 6 is BF14, if we're going to be complete. Whether I do this or do this, this is the layout. Okay? So what difference does that make? Well, that means if I wanted to print all these, I could just use a pointer. Right? Among other things. It also helps to understand. And also, while we're here, let me point this out to you. This is in C, as well as many other languages. So in C, multi-dimensional arrays, are stored row-wise. That means even though I see it as multiple rows, the second row is right after the first row because here's where my second row begins, and so forth. Some other languages do differently. So in particular, in Fortran and MATLAB, they do it column-wise. Which means if I wrote code that looked similar to this, I would have 1, 4. They would still all be on a row, but the first number would be 1, the second number would be 4, the third number would be the 2, the fourth number would be the 5, the fifth number would be the 3, and the last number would be the 6. So knowing the difference between these actually can come in handy sometimes. So while we're here, how does this actually work? This is where the pointer arithmetic comes in handy, or is used. When you say go to the second row, which has index 1, that's saying jump over the size of one row to begin at the next row. If you say go to the third row, which has index 2, it's just jump over each of the first 2 rows to then get there. That's how that works. So back to what I was about to show you here. Actually, I could have left all that in there. It doesn't matter. I was trying to get rid of the stuff we don't need so we can read it or easily see it. Now, if I write this right here, I'm going to have a problem. Let's see what that looks like before we see how to deal with the problem. Initialization from incompatible pointer type. All right. What did I say? Well, I said it somewhere else. All right, another video, I think. But when I write the name of the array, which in this case is X, I get the address of the first element of the array. Right? Which is kind of what I'm alluding to here. This is an array of arrays. So that means this is the first element of the array. And what is that? That's not an int. That's an array of 3 ints. So this is the wrong pointer type for that. All right? So an easier way to do that would be to do this. Address. Well, there's several ways to do it, but let's do this. All right? So now I have the address of the first element. Because x00 is the 10, then I get the address of the 10, which is where we want to begin. So think about what we just printed a moment ago in one of these. And I want to increment the pointer after I use it. I changed the orders a little bit. Let's just put it back in the same order, actually. And there's those numbers right next to each other. So my pointer just goes from here to here to here to the 4 to the 5 to the 6 because they're in contiguous memory locations. If they were truly stored as some type of two-dimensional construct, which your memory in your computer is a two-dimensional construct, but if this were stored this way, then I would have to have some way of knowing how to take the pointer and jumping down a row and back to the beginning of the second row of numbers. But here I don't need to do that, obviously, because they're really right next to each other. I just need to know where it gets started and where to stop. So let's look at this now. So when I say the address at the beginning of the entire array is the same as the address of the first row of the array, which is the address of the first element, that's true. So if I say, where is this two-dimensional array? And let's say that the 1 is at address BF00. This two-dimensional array, this 2x3 array of ints, is stored beginning at BF00. If I say, where's the first row of this array? It starts at address BF00. If I say, where's the 1? It's at address BF00. But those 3 different things represent 3 different objects. So if I had a pointer to either the 1 or the first row or the entire two-dimensional array, incrementing those pointers would move us to different locations because of the pointer arithmetic. So let's look at some stuff. So we say, okay, address of data is 8140. What's the address of row 1? That's also row, or excuse me, 8140. That's the first row. And finally, if we put another set of stars, we just get the first number. Let's try to understand how all this works. So the general form for getting the address of any element of a 2D array is this. Take the array name and add the row offset. That is, how many rows down do I want to go? And it's making use of pointer arithmetic. So this would add, if I put a row in here, it'd be row times size of a row, amount of spacing, add that to this address, then I dereference that. So I like to think of it as sort of locking that in. So now when I add the column offset, now we're figuring out how to move along column. So doing this right here helps me move down rows, then I add the star, then I start moving along the columns. But this entire thing, if it's talking about a two-dimensional array or greater, is an address. So this right here will give me the address of a number in the array. And this right here in pointer notation is equivalent to this in subscript notation. Data 1, 2, and then give me the address of that. If I want the element at a particular location, then here's my form. How many rows away from where I begin should I go? Lock it in. How many columns away from that along that row do I want? Lock it in. By this point, I know which row column offset contains the number you want. And so this second star, the one on the outside, gives me the actual number at that point, if this is a two-dimensional array. So when I write this right here, this is equivalent to writing this right here. And actually, this is equivalent to this, regardless of whether it's a two-dimensional array or a three-dimensional array or whatever. If this were from a three-dimensional array, this would be an address, and this also would be an address. So let's revisit that original problem. When I first learned to program in C, and I would see things like this, I didn't understand really the true relationship between the stars and the array names. So I thought it was about memorizing, oh, when you see one star, it means this, and we see two stars, it means this, and so forth. But that's not the case. If cells had been a one-dimensional array, writing star cells would give me an int in that array. But since cells here is a two-dimensional array, this gives me the address of a row in the array. So what do these actually mean? Well, think about what we just saw in the previous slides. Star cells really means cells plus 0 dereferenced. So what does this mean? Well, it says starting at the first row, move 0 rows away, so I actually stay on the first row, and now I dereference it to get the address of the first row. And I also could write it this way. When I see star star cells, that's the same as saying starting at the first row, move 0 rows down, dereference, so I'm still in the first row where the 1 is at. Now move 0 columns to the right, which means I'm still at the 1. When I dereference that, I finally get the 1, which I could write it this way, cells 0, 0. So understanding this will help you, especially when you get to dynamic memory allocation. But it can also help you in certain strange situations involving pointers. So what about, and this has an issue here, but we can create pointers to two-dimensional arrays, one-dimensional arrays within a two-dimensional array, or and so forth. But we have to figure out what we want to do. So here I've created 3 different pointers, and every one of these technically is going to get the same address. So here I've created a pointer to an int, and so it's going to contain the address of the 31. This is a pointer to the first row, so it contains the address of 31. This is a pointer to the entire two-dimensional array, so it has the address of 31. But how these will function differently will be that when I increment pointer 1 by 1, I move to 32. When I increment pointer 2 by 1, I move to the second row. When I increment pointer 3 by 1, I move to what you would think might be the third row, which is where the beginning of another two-dimensional array would begin. So why are there parentheses here? So I'm looking specifically, say, at the second line, but they're also here in the third line. Why write int parentheses star pointer to close parentheses instead of just int star. This right here overrides the default precedence. So if we look at the precedence table, we can see that the array subscripting brackets have higher precedence than the star. So what that means is, when I write this second version, it sees the square brackets as touching pointer 2 first, so it thinks what you're doing is creating an array called pointer 2 that consists of 4 elements, each of which is a pointer to an int. This one forces the star to touch first, so it says you're creating a pointer to an array of 4 ints. So this is a pointer to an array. This is an array of pointers. Let's see this right here. Let's write some code to work with that. So we'll write something similar to that. Doesn't necessarily have to be the same thing. And D. We'll make it 2 by 3. And I'm going to put my other set of square brackets here, or curly brackets, excuse me. P1 will equal the address of the first element. That's D00. And now we have 3 elements per row. Sorry, that should be this. Why can't I just write D? Because since D is a 2-dimensional construct, it's an array of 1-dimensional arrays. So writing just D causes it to give me the address of the first element, which is a 1-dimensional array, which is what this is. Oops, that's still wrong. Let's do this. And we'll make these the addresses. So %P, %D. Let's check that before we move on. I like to do things incrementally, so I want to make sure this is working before I mess up something else, potentially. So there's my numbers, there's the addresses, and mainly what I want to see is where things are at. So let's do this. So we'll start with P1. So dereferencing P1. I need the address first. And actually we'll just do this. All right, so what do we see? When I wrote P1, which is supposed to contain the address of the 1 here, it has address 60, which matches what was here. When I increment it by 1, it moves to the next int, which is the 2. 2 has address 64, so I get 64. All right. P1 is a pointer to an int, so by incrementing that, I move to the next int. Let's see what the next couple do. Now P2 points to a row. All right. And sorry, I forgot to increment that. That's P2. All right, so this right here, so it says that P2 contains address 50 initially. What's address 50? Well, that's where the 1 is at. And then when I increment it by 1, it moves to 5C. 5C is the 4, so that's the second row. So since I pointed to a row, incrementing moves me to another row, and then moves me to another row, and so forth. Let's see the last one. Using P3. All right. So the addresses have all changed again because I ran it again. But we see 1 is at B20, 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 B20. So now pointer P3 initially contains the address of the 1 because that's where the entire array is. All right. But then when I increment it by 1, it goes to 38. Well, what is that? Well, the 6 has address 34. So if I were to put another 2x3 array of ints right after this, it would be 4 bytes past that. So 34 plus 4 is 38. So I incremented that. This is why it's so important that when you have a pointer to something, it points to the right type of thing. Every one of these, there's 20, 20, 20, 20. Every one of these 3 pointers initially points at the location of the 1. But conceptually, they mean different things. Here we're talking about pointing at an integer. P2 points at a row of 3 integers. P3 points at a 2x3 array of integers. So by incrementing, you move a different amount. All right. So hopefully this gives you much more insight into how pointers and arrays work. A lot of what I was showing you here really had less to do with pointers and more to do with addressing, but it's all important to understand. And as I stated earlier, you could probably actually get by without knowing this much to do lots of things. If you just say, I want to print an array, sure, you can do that. And if you do simple pointer stuff, you can avoid what I've taught you. But it will give you much more knowledge so you can do things with dynamic memory allocation that may not be clear at this point in the course. And also doing just some weird things with pointers like what I showed you here would be difficult to do without understanding this. So my next video will move on to strings, and we'll see that a lot of the string library functions actually make use of pointers. So we will need to know how to use pointers just to do a lot of things involving strings.